Good morning. This is Mr. Herman. This is going to be our final installment of these 3 videos for Chapter 10, Day 4. And we just looked at our significance tests for difference in two means. And now we're going to look at confidence intervals for difference of two means. Okay? So let's go ahead and look at this formula in our conditions. Okay? So the formula for a 2-sample t interval for mu1 and mu2 minus mu2, what are the conditions? So here's our formula first. We'll start with that. X bar 1 minus X bar 2. There's our statistic, or sample stat. Plus or minus T star. There's our critical value. And then here's our standard deviation of statistic. S1 squared over N1 plus S2 squared over N2. And we saw all these before. Is this on the formula sheet? Like we've said on a lot of these, kind of. Okay, bits and pieces are conditions, random, 10%, LCC for both. Okay, remember if on our LCC, when we're dealing with means, we get X bar, so that's our means. If we don't meet our threshold by the central limit theorem, that we have to show that there's a no skew and no outliers. Okay, and we might have to do that here, i.e. we will have to do that here because we haven't done it yet. Okay, so we have a example about chocolate chips. We're comparing Chips Ahoy and Great Value brand and the number of chocolate chips that we see in each cookie. Okay, so we're going to construct and interpret a 99% confidence interval for the difference in the mean number of chocolate chips in Chips Ahoy and Great Value cookies. And then we're going to see if our interval provides convincing evidence that there is a difference in the mean number of chocolate chips. All right, so let's go and start with our state. We're doing confidence interval, so our confidence level is 99%. Okay, let's define our parameters. So we're going to have mu c, I guess mu c a. You could probably just use mu c. So that's going to be the true mean number of chocolate chips in Chips Ahoy cookie. We have mu GV, you could probably just say mu G, which is the true mean number of chocolate chips in Great Value cookies, or in a Great Value cookie. Okay, now like we saw in our proportions, if we're doing confidence interval, we need to make sure that we show what is our difference. So I'm going to say mu CA minus mu GV. Okay, if you do it the other way around, that's perfectly fine. Your answer is going to look a little bit different. It should just be a difference of positives and negatives. All right, let's see. Let's go ahead and move on to our plan. Okay, and our plan. How many samples? We have 2 samples. Okay, we have means, so we want to do a t, or an interval for difference in means. All right, so let's go and check our conditions. Random. Okay, we are told that we are randomly selected, stated, and populations are independent of one another. Okay, we know they're independent populations because you can't be a Chips Ahoy cookie and a Great Value cookie at the same time. Okay, let's see. Let's look at our 10%. It is safe to assume at least 100, because we did, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Cool. At least 100 Chips Ahoy cookies and Great Value cookies. Okay. Our LCC. Oh, that's not true. That's not good. Okay. Now we need to go ahead and check on our LCC. So let's go ahead and make some dot plots. Okay, I'm gonna make a double dot plot. So here's our Chips Ahoy. Let's see, our low is 14 and our high is 26. Okay. So 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Okay, so Chips Ahoy and then great values below it. Let's see, we got 17, 19, 21, 16, 17, 18, 20, 17, 18. That looks pretty good to me. No outliers, no major skew. Let's see, great value. We got a 22, a 20, 14, 17, 21, 22, 15, 19, 26, and 18. Okay, bit more spread out, but once again, doesn't look like there's a much major skew. So no major skew, no major outliers. So that meets our normality check for LCC. Okay, so let's go ahead and do the do. Okay, do. Now, since we have data, we need to make sure we enter our data. Stat edit. You're going to go ahead and I already did that beforehand. I just put all of my Chips Ahoy in L1. I put all my great value in L2. Okay, and then I'm going to go ahead and hit stat. Go over to tests. And we set a 2 sample t interval for difference in means. So I want a t interval and it's 2 samples. So 2 sample z int. Okay. Now I have data. Oh, made a mistake. I picked z int. That's not good. 2 sample t int. There we go. I've got data and I'm not afraid to use it. L1 and L2. Okay, Chips Ahoy is my first column, great value is my second column, which matches what we said for our difference here. If you set a different one, make sure that your L1 and L2 match up. Frequency is when we're not going to touch that confidence level. We're going to say 0.99. Pooled, we said no, do not pool. And then calculate. Okay, there we go. So, just had to write down a couple things on our do portion. Let's write down our confidence interval. So negative 4.814 comma 2.8138, and then our degrees of freedom 13.1. Cool. All right. Now let's go ahead and conclude. We are 99% confident that the interval negative 4.814 to 2.8138 captures the true, let's see, true difference in mean number of chocolate chips between Chips Ahoy and Great Value cookies. Okay. All right. So let's look at question B. So that was A. Let's get B. Does your interval provide convincing evidence that there is a difference in the mean number of chocolate chips? Here's that word, is a difference. Okay? Is a difference means not 0. Okay? If you look at our interval, could we have 0? Yeah, because we have a negative here and then a positive, so it could be 0. So we don't have convincing evidence since 0 is in the interval. Okay, and it probably wouldn't hurt here to say we don't have convincing evidence that the mean number of chocolate chips is different since 0 is in the interval. Okay, and in that context is always a good thing to do. All right, so let's go ahead and talk about t-procedures for a bit to finish off chapter 10. Okay, so should we use t-sample t-procedures with paired data? The answer is no. Okay, the answer is no. Okay, now why not is because the relationships between the data matter. Okay, data in each sample are related to each other. Okay, so that means that if I have, it's like if I were in the cookie example, if I picked 2 cookies and they were really similar to each other, it's like, oh, it's the first cookie in the batch. Then if I was checking that first cookie in the batch, okay, matched pairs is essentially what we're thinking of here. Is, oh, if I were to, let's see, what's a good example? Well, also an example that we're looking at below is testing with distractions. If I take the test with distractions and then I take it without distractions, we want to see, did I have a difference? Okay. So now, how can we know which one to use? So if we have 2 sample or paired, okay, this is randomized completely. Okay, whereas in a paired, we can pair and split our data. Okay, we're going to use the same subjects in paired data. Okay. In a 2 sample, what we're looking for is looking for the mean difference. Or, oops, made a mistake. 2 sample, we're looking for the difference in means. In paired data, we're looking for the mean difference. Okay? So paired data, we essentially are just getting one value. This is difference in means, so I have 2 groups that I'm taking the means of. In paired data, I have a bunch of means that I got because I took the difference in them. Okay? We can talk about this more in class if we're confused on the difference between 2 sample versus paired. So let's go look at an example here where we're going to figure, okay, we're going to describe an experiment for a 2 sample t-test and then design an experiment for a paired t-test. Okay, so we are looking at distractions versus not distractions. We've got access to 2 classrooms and 30 volunteers who are willing to participate in our experiment. Okay, so if we're doing a 2 sample t-test for our inference method, let's see, I'm going to randomly assign 15 to a distraction room and 15 to one without distraction. Okay. Test each. Then compare the mean scores from each room. So I randomly assigned my 2 groups, and then one had distractions, one had not distractions. I look at my scores, look at the mean score in the distraction room, mean score in the no distraction room, and compare. Okay? Now, if I'm designing an experiment so that a paired t-test would be the appropriate inference method, it's a little bit different here. Okay, still going to randomly assign 15 to distraction room and 15 to one without distraction. Test each, then swap rooms and test again. Compare each individual's score. Okay, so in this situation, randomly assigned 15 to distraction room, 15 without distractions, tested them, and then said, okay, now you're not in the distraction room if you were first, and now you are in the distraction room if you weren't first. Then I'm going to compare each individual score. Now, which design is better? Hopefully, you said the paired t-test. Okay. We eliminate variability. And we do that in test score. Okay, so if we've got someone who's just inherently bad at taking a test, and regardless of whether they're distractions or no distractions, they would do poorly. That doesn't necessarily come out in the 2-sample t-test, but if they get a score of 10 and the distraction remain a score of 11 without distractions, that's not much of a change. Okay, but 10 could be just a super low, a super low score if it were in one room or the other in the same 2-sample t-test, whereas we're just looking at the change of 1 in a paired t-test. Okay, so we eliminate variability in test scores. That's based on room. And then what does that do for us? That gives us more power. Gives us more power. Okay. What's the purpose of random assignment? Okay, so random assignment here, we're doing that to differentiate between distraction room and the room without distractions. Okay, so it makes sure that environment isn't favored based on always going first or second. Okay, so we don't have everyone taking the test first with no distractions and taking it with distractions. We're able to put in that element of non-confounding to prevent confounding. Okay. All right, so if you still have questions, feel free to ask those in class today.